where we have an angle of incident and an angle of reflection in equal, and we'll get good internal. And then we have good transmission of the light. All this starts with, there's nothing you can do in that core if the core is has impurities in it, or the core is not ideal. There's nothing you can really do but replace the core. What is the key? Is putting the light in. We got to put the light in properly. If we put the light in properly, then it will propagate properly. Let's see here. Different types of multimode exist. Step index, what happens to the output pulse as you go so far? You can see that it's doing what? Smearing, right? So this, obviously we send it in nice high powered, but yet on the end it's flattening out, it's smearing out, it's widening. It's going past its spectral bandwidth. If it goes past its spectral bandwidth, it could actually get into somebody else's channel. Well, then that's a problem. And that can cause OBI, because you're actually beating into another channel, and if two channels are talking on the same channel, you get OBI. That's the... This one, that they've created graded index multimode, and look what happens. How does it look on the other end? Looks better, right? It's not ideal. Looks a heck of a lot better than the first one, right? So graded index multimode, there's two different kinds. So when you're looking for multimode fiber, look for the graded index, because you're going to get a better throughput through multimode. And then here's single mode. Same distance, if we actually compare the distance against multimode versus single mode, and if we're all sending the same pulse in, you can see that multimode looks really good. Versus multimode, it doesn't go as far. So how far does multimode go? What's typical jumper size? About 100 meters, 200 meters. I mean, I have longer than that. But it's more short distance. In a short distance, this is what happens to the signal, or the light. In a short distance, nothing happens. Pretty much, it almost looks like the exact same symbol we put in. That's multimode. Nothing really here new. Seems just kind of going a little bit more about that. This is just showing you cutoff wavelength is when only one wavelength can propagate. Once you get to 1200 nanometers, these are actually a range, 1200 to 1250 nanometers. Once you get there, you can only propagate one version of light. So multi-mode, as long as you're under the cutoff frequency, you can do more than one. And in order to do multiple versions of light past the cutoff frequency, you need to do what? Multiplex. You got a multiplex. So that's where the multiplexer comes in. It'd be nice just to have fiber that could take several modes, but we wouldn't get 20 kilometers out of it. So what is the wavelength for cutoff? Once it goes through the cutoff, it starts acting like multimode, or once it hits the cutoff, it stops. It only propagates one version of light. Which wavelength would that be?
Say that again?
So basically, what is the wavelength that once it's past that wavelength, you can only propagate one mode of light?
That it goes from multi-mode to single mode?
Well, not quite like that. It's really where you can only propagate one version of light. What is the wavelength? Above what wavelength? I'm asking it incorrectly.
Well, you said above 1250.
Yes, so it's that one. You got it. So anything above 1200 to 1250, once it gets above that, we can only propagate one mode of light. So that's where you have to multiplex. So that's why multimode uses a wavelength less than that, and typically it's 850. Mode field diameter is your beam width. So obviously the core design and ovularity and the concentricity, all that gives you a nice mode field diameter, nice beam width. So the idea is the cleanest beam width we can get going in, the cleaner it would look on its way out. So that's what's mode field diameter. And you can get these specs from the manufacturer of your fiber. I do have a little Eris cookbook, remind me, little pocket guide in PDF. I'll put up there, and they got a whole bunch of fiber stuff in it. This one here is your light gathering ability called Numerical Aperture. And we saw this one earlier. It's again has to do with cone of acceptance, which is bringing the light into the waveguide and they refer to that as light gathering ability, also known as numerical aperture. So you might see all these specs when it comes to fiber. You're like, wow. Anybody realize that all this existed for fiber? Yeah. So if you worked with fiber, you're like, yep, I remember all this. So that was it for that lesson. You want to do the other fiber one, and that way, and then we can go through the other fiber chapter. Then you can do the 2 fiber quizzes together and take a break and all that. Okay. Questions? Any questions on that? Probably thinking to yourself, why do I have to know all that? Well, let me tell you this. If it makes you feel any better, the 25-question quiz at the end. When I sat down with Time Warner, there's very few questions from this chapter. Most of it is everything we covered in the first day. Because a lot of it is, again, you're not going to need all this knowledge out there to support RFOG and EPON. You might get, out of these 2 chapters, maybe 2 questions. For example, what's the difference between multimode and single mode? I should know that. That's a basic thing. I am not going to ask you questions like, well, what's the difference between the angle of incidence and the critical angle? I mean, that is nice to know stuff, and if I need to look it up, I can. So here has some optical safety in here. I'll show you some of the different types of fibers, and we'll talk a little bit about the characteristics of fibers. So what's one characteristic of an optical fiber that you have to worry about, that we've been talking about? Starts with a D. Dispersion. There we go. There we go. We talked about dispersion. Dispersion causes another characteristic called, starts with an A. Attenuation. Yeah, we haven't talked about absorption yet, but kind of did. So yeah, we talked about dispersion. That's a characteristic. We've talked about attenuation. That's a characteristic. Those are probably the 2 key areas we're going to worry about. I'll show you some other ones. Here's all the different parameters, all different things that we worry about. A lot of those things, there is intrinsic characteristics and extrinsic characteristics, so I'll talk about those. Some that you can control and some you can't. You can definitely control, you can't stop attenuation from happening, but you can reduce it. There's ways to reduce it by not macro bending, by using clean fiber connections. Let's kind of take a look at some of these. Some of these we've kind of talked about. Attenuation, I've added some red just to kind of... Every fiber is going to give you attenuation. So depending on the manufacturer of your fiber, it has different attenuation factors. So if you started buying something different from maybe you started buying Comscope fiber, and you're supposed to use a 0.25 dB per kilometer, and now might be 0.24 dB per kilometer. And so what's the big deal? Well, I mean, that's your headroom. So if you have an extra 0.2 of headroom, you're like, well, 0.2 dB is nothing, Steve. Well, that's probably a good 4 fusion splices. That's huge, actually. So just little tiny changes like that actually affect your headroom. It actually affects the design. So it's good to know these things. If you're going from one fiber to another, they're going to attenuate different. So knowing that, okay, how much old fiber can I keep versus new fiber? And by knowing that, so you might do that, or say, you know what, there is no scenario. I got to change it all. Cutoff we talked about when it's not single mode fiber anymore. Mode field diameter, we talked about that. And there's modal dispersion. This is called mandrel wrapping. is a technique that you can reduce modal dispersion. That's not going to affect us. This is performance. There's actually different types of tests that are run on fiber optics. You could go back to that standard I shared in chapter 2 if you wanted to find more about, the performance factors and how they're calculated by the vendor and how kind of some of the tests. I mentioned one, a fiber proof test, which is the strength of your fiber. I talked about ovularity or concentricity, core to clad offset. All these values are very, very important in the design. So you can see a core to cladding offset is 0.05 microns. There's also other factors you'll read in the notes, curvature. If you have too much curvature in the fiber, it will curl. It's called fiber curl. All these things are very, very important because construction of fiber and maintaining good signal. It's complicated. It's usually not. If you buy products to start with, you're going to have a good quality. Attenuation, scattering. They mentioned scattering. There's actually all different types of scattering. I won't go into all the different ones, but there's Rayleigh scattering. There is double Rayleigh scattering, scattered light, and all kinds of different scattering. Scattering is when, well, you tell me, what is it?
I guess light just seems to go in all directions.
Yeah, and what causes the light to go in all those different directions?
Well, usually refractions.
It's usually something in the impurity.
The
in
impurities?
the fiber that it hits and just
Yeah, so if it hits that glass in the manufacturing process, maybe have an impurity there, and it hits that impurity, it just goes everywhere. Well, some of it's going to come back, and that stuff that reflects back to us is going to actually attenuate the signal. But it also could happen at the connector. How could it happen at the connector? Was it the connector was manufactured incorrectly?
it's not aligned properly.
That, or it
Could be not aligned. What is it?
could be dirty.
Dirty. Just clean off in your shirt. Good, right? Well, what was interesting about Jason, what he showed, he cleaned it, and there were still problems. What happens? Sometimes you clean it, you get the dirt out of it, but there's scratches now, and you can't get those out. And those scratches could also scatter the light. So sometimes the connector is just too far gone. You can clean it all you want. Now you can see there wasn't dirt. He had like cuts in the glass, and you're done. And so in that case, we're going to have to replace that connector or replace that jumper because that happens. Well, I only rubbed it off my shirt a couple times, but I could have scratched it. Yeah. So yeah, that's what we're showing there, scattered light. And the interesting thing about a PDR, you got light. And what happens when it hits those imperfections, light comes back, and we measure that light. And then that tells us where there's imperfections in the fiber path. We have, obviously, bend loss, talked about that. Dispersion, reflections, there's one, they call them Fresnel, no S, Fresnel reflections. Probably heard of the Fresnel zone in Wi-Fi. But it's an area that, not in the Fresnel zone. What happens is you start losing light. Here, this is more of a reflection. The actual reflections are called after the cycle, if you wanted to know. And then scattering, we covered that one. So all these things will ruin our light. And there's the macro bend, obviously, we talked about that. Don't be confused with a micro bend. We'll talk about that. So dispersion, covered this. Spreading, I don't think there's anything more we can say about that. You have something to say? Here's 4 different kinds. Again, if you're working in the hub and you're working with multi-mode fiber, long distance, like I'm just going to buy new jumpers that are even, then you're going to start getting into modal dispersion. So you might want to do a little research first. You know, how's this length? And just that would be an easy fix. Chromatic, this is one we have to be aware of and just know it exists. Waveguide, I'm going to talk about that. But that's where light travels in your core and your cladding, and then polarization mode, the different polarizations of light actually mix together. So here's chromatic. 3 different wavelengths. We'll just call them different colors. Send them through the fiber. Guess what happens? They arrive at different times. So this kind of stuff happens. All of a sudden, what happened to our wavelength? It's not even there. These two are overpowering it. So we actually lost the wavelength in that scenario. So that's really, there's some formulas around that, but it's basically the velocity of light of each wavelength in the waveguide causes that. And it could be a distance, you're going too far. It could be the type of transmitter you're using. Some transmitters only go so far. And it could be a lot of it's to do with craft. This is the waveguide. If for some reason your core is this, and the other core is that, now you're shooting light into the cladding, and you're shooting into the core. Then on the other side, you could get multiple copies of light depending on the connection on the other side. But that's what waveguide is. It travels at 2 different velocities, so you get copies of light. And pretty, that's a mating issue, just trying to make sure you have it mated. And this is showing electrical Y and X axis. And what happens if there's delays in it, you can see that the electrical signal kind of gets manipulated. Polarization issue. The same thing can happen in light. This is typically high speed. The book talks about 10 gig. Whereas the polarized light pulses actually merge with one another. So if you're using polarized light, that will happen. And that could happen over 10 gigs. So I'm sure you'll do some testing and make sure that's not an issue. Just more information. Not an issue until 10 gigs, and you might see that start cropping up. So I think we covered dispersion. Again, these are pulses, and you actually see they're spreading out and they're actually overlapping one another. So the more pulses that we send, wider bandwidth, more dispersion. So the wider the pulse, the more dispersion you're sending through.